changing my role, as you can all see. So I'm moving from conference organizer to chair for the next session. And so it's my pleasure to introduce Pavel Kurasov, our next speaker. So Pavel did his first PhD in 1989 in Leningrad with Boris Pavlov. And then he moved to Sweden and did another PhD in Stockholm with Jan Boman in 1993. He then spent quite a few years traveling around Sweden. So he went to Luleå, Lund, spent a few years as a Humboldt Fellow in Bochum and Bonn during that time, and since 2011 he's been a professor at Stockholm University. Pavel's a quite prolific organizer of conferences, so you might want to update your CV on your webpage. So as the last one I could see there was 2014, so by 2014 you'd already organized 13 conferences, and I know there were more after that, but quite a few of you here might be aware of the OTAMP series of conferences, and Pavel has organized several of those. Now, most of his work, certainly in recent years, has been on quantum graphs or metric graphs, and there's a wonderful book that you can see over in Simpson on this, so go and have a look at that. And, well, today he's going to tell us about how you get from metric graphs to Fourier quasicrystals. So, thank you very much, Pavel.
So, can you hear me? Is it on? No, now, yes. Good. First of all, I would like to thank the organizers for a very good organization of this conference. I think that organization is so good that people started to complain about the weather, which is outside the control of the organizers. But I was thinking that maybe they simply tried to get the best weather, but tried a little bit too hard. Okay, and then you see, giving this talk, I was thinking about Heinz Langer, who passed away recently because he was extremely kind to other my works, and I'm afraid that I'm a little bit unsatisfied that I didn't manage to tell about this work to him. But this work that I'm going to tell you is joint work with Peter Sarnak. This is approximately 2/3 of my talk. And then in the last, I hope to speak about recent developments that we did with Lior Alon, Mario Kummer, and Xynthia Vincent. Yes? And also, you see, I have a little bit too many slides, so that's why some of the slides I will jump over. But nevertheless, try to ask questions. Okay, so first of all, what are quasicrystals? Yes. So I think that many of you have heard about this, but this is an area where there is no complete order. So you see, this is an attempt to generalize the notion of the solid state. One should think about solid state consisting of atoms, and atoms are points in the space. Yes. And then the first assumption described in such state that we need to take is the following, that it's uniformly discrete. Uniformly discrete, it means that there is always a finite distance between 2 points. So there are no points at arbitrary small distance. On the other hand, these points should be not too sparse. So it means that every big ball of big radius should contain at least 1 point from this set. So, and they are called Delaunay sets. Sometimes they are written like this, but Boris Delaunay, one of his ancestors was a French general who stayed in Russia after Napoleon campaign. So this is more correct spelling. Yes. And we define the ideal crystal, which will not be interested today at all. as follows. So an ideal crystal, this is a set of points that can be obtained as L plus F. L is a certain full rank lattice, and F is a finite set of points. We take a finite set of points and we shift them in accordance to this lattice. And for this ideal crystal, it's a perfectly ordered system, and for it you have a Poisson summation formula, so which is written here. Yes, this is written just for the z to the power d, but of course if you have a set here, you can generalize this formula. It will be a finite sum of such formulas. Yes, but this formula can be written also in this form. So if we introduce a measure mu, which is a set of delta functions at integer points, then the Fourier transform of mu will be also a set of delta functions at integer points. Here you need to choose the Fourier transform carefully, so that there are no coefficients. Okay, but people try to generalize this, and first of all, of course, the physicists, they were first, so to say. Well, not really, exactly. Not really, actually, in this case. But, for example, Shechtman and Steinhardt, they introduced quasicrystals. And these are systems which don't have, which are not periodic, but have some kind of order. So for example, they can be found in some meteorites. Yes, this is a very unusual state of nature. So somehow in this system, somehow locally, you know how to construct the system, but globally you don't have periodicity. Somehow, and I can recommend any of you to find a lecture by Steinhardt, where he explains about his discoveries. Okay, but in mathematics, actually, the first quasicrystals can be found in some mosaics from the 15th century. Yes, so in the Central Asia. But mathematically, the first one were Wang and Penrose, and here this is a Penrose tiling in front of Andrew Weil's building in Oxford. So this is a system where this is a tiling, and there are only two different tiles. Yes, but you manage to tile the whole plane. Yes, so and you can see that locally it looks perfect. Yes, but there is no periodicity. Yes. Then in mathematics, of course, there were works by Harald Bohr with almost periodic functions, and not only Harald Bohr, but also Bisikovich and so on. So this is also an attempt to generalize periodicity. Yes? But for us, it will be interesting these cut and project sets, or Meyer sets, which he introduced and studied since 1972. So here's an example. So take a lattice in two-dimensional space, and then take another frame, which has an irrational angle here. Yes? So then, in this new frame, you take how is it called? The area band. Yes, you take a band, a strip. Yes, and then you consider all the points which are on this strip. Yes, and then you project it on this axis. You get a set of points. Yes, and this set of points is was called cut and project or Meyer set. It has the following interesting property that it can be Delaunay, yes, but its Fourier transform will never be discrete. Somehow it will have support on a dense set of points, because the support of the Fourier transform will be on the, you take vectors from the dual lattice and then you project them on this axis. And then it will always be a dense set. So then there was another suggestion by Galiulin from Moscow. He suggested that introduce quasi-regular sets. He said that quasi-regular sets are Delaunay sets, such that the difference is again a Delaunay set. Surprisingly, it appeared that these two constructions are the same. Yes, so it was proven by Lagarius few years later. So it means that for us, quasicrystals is a Delaunay set such that the difference of lambda minus lambda is contained in lambda plus f, where f is a finite set, or equivalently these other two definitions. Yes, and what I already said, for these sets, you have a Poisson summation formula. So if you introduce the measure mu with the support at the points from this set, then the mu hat will have a support on a dense set. So, and this is not very good. So therefore, the question is it possible to do better? Can one do better? Okay, and here crystalline measures appear. So they were introduced by, they were popularized by Meyer. So the definition is as follows. A crystalline measure is a measure, atomic measure, such that it is a sum of delta functions, and its Fourier transform is also a sum of delta functions. Both have discrete support. Discrete support means that every interval, compact interval, contains finitely many atoms from these measures. Yes. So, and here, important thing that for this to hold, both sets, lambda and s, should be well structured, like in Poisson summation formula. They're simply periodic. We are not interested in periodic examples. Yes, so they are called trivial crystalline measures. So people also studied Fourier quasicrystals. So here, this, of course, for this to hold, this mu should be a temperate distribution. So it means that these coefficients should not grow too fast. Yes, but also one introduces Fourier quasicrystal. This is a crystalline measure, such that not only mu and mu hat, but also absolute value of mu and absolute value of mu hat are temperate distributions. So, and they define simply by taking absolute value of the coefficients. Okay, in the 50s, Kahan and Mandelbrot, they studied these crystalline measures. So it means it was before Meyer, but without any concrete examples. And if you want to construct crystalline measures, then there is a negative result. Negative means that it shows how why this is hard. Because Lev Alevsky, they proved that if the support of both the measure and its Fourier transform are uniformly discrete in one dimension, then the corresponding summation formula is just a sum of Poisson summation formulas with the same period. So this is a trivial crystalline measure. And Yves Meyer told me that his working hypothesis was that such non-trivial crystalline measures don't exist. But in recent years appeared several positive examples. So there was an example by Lev Alevsky, but not explicit. All these examples either are not explicit or the corresponding measures are very specific. For example, in this Radchenko-Vizovska example of, connected with interpolation, these measures are supported by the point square root of n. Yes? And actually they are not uniformly discrete, because at infinity the distance between the points becomes smaller and smaller. So, and you see, I didn't know about this story. Yes, I was working with metric graphs. Actually, somehow by this talk I want to attract attention to metric graphs, because I think that operators of metric graphs can lead to some other interesting results as well. Okay, so what are metric graphs? You consider a set of intervals of the real line, yes, and you connect these intervals at the vertices. On the intervals you consider, for example, second derivative operator, yes, but to make it self-adjoint Hermitian and so on, you need some vertex conditions. The standard way to introduce these conditions is to require that the function is continuous and the sum of derivatives, but here you have to take derivatives in the direction from outside the vertex. Yes? So the sum of the derivatives is 0, so-called Kirchhoff condition. So it means that you want to treat this object as this graph as a geometric object. Therefore, you don't know how you parameterize the intervals. So it's independent of the parameterization. Only the lengths of these edges play a role. So how to calculate the spectrum of this graph? So to calculate the spectrum, you have to solve this equation, second derivative of psi is equal to lambda psi, and ensure that vertex conditions are satisfied. On the edges, this is a trivial thing, so this is a combination of exponentials, but you can write it in two different ways. The first way, the red one, this is like the waves coming into the edge. And the blue way looks like the waves coming outside the edge. Yes? And of course, the amplitudes are connected. So the first connection is very simple, because on every edge, somehow this amplitude is equal to this one multiplied by such a coefficient. Yes, and the same there. So it means that to get blue amplitudes from red, you have to multiply the vector of all amplitudes by the matrix, diagonal matrix with 2 by 2 matrices on the diagonal. They depend only on the lengths of the corresponding edges. This will be important in the future. The second condition comes from the vertex, because in the vertex you have waves that come into the vertex, then you get from the vertex condition you get the waves coming outside. So these are unitary matrices, yes, and they have the form that if you take all amplitudes connected with one vertex, you have a unitary matrix, and then you have another unitary matrix connected with the second vertex, and so on. And then, of course, if you multiply these two matrices by, then you get red amplitudes back. So because H scattering matrix maps red amplitudes into blue, but vertex maps blue amplitudes into A. So it means that this matrix, this product of these matrices has an eigenvalue 1. This is the characterization of the spectrum. So I can write it like this or like that, because SV is not only Hermitian, but it's not only unitary, but also Hermitian. Therefore, we can write it also in this way. And this will be our secular equation, which determines the spectrum of this graph. And you see, the entries of these matrices are either constants, yes, or some exponentials. Therefore, this matrix has entries constant and exponentials. When you take determinant, you get a trigonometric polynomial, sum of exponentials, yes? And this trigonometric polynomial has only real roots, because every root corresponds to an eigenvalue. Hermitian operators usually have real eigenvalues. So therefore, you can see that it smells the theory of almost periodic functions, because almost periodic functions can be defined as a limit of trigonometric polynomials. So then we shall prove the trace formula. So I don't want to go through the proof. I just indicate what you can do. You take this equation. Yes. On the left you have an analytic function with zeros on the real axis. You take logarithmic derivative of this function and you integrate the jump of this logarithmic derivative on the real axis. So then from the left hand side you will get sum of the delta functions and the zeros of this function, of this analytic function. So this is the spectral measure. Yes? On the right hand side you have determinants and so on, and you use just elementary things like logarithm of the determinant is a trace of the logarithm, then you expand logarithm in a series, because outside the real axis SE is subunitary, so it has a norm less than 1, so the series is perfectly converging. But when you calculate the trace, you get a periodic orbit. Why? Because what is the trace? You take amplitude, for example, corresponding to this, to wave coming in, then you multiply by H scattering matrix, you come here, vertex scattering matrix, you come there, and so on and so on. And then the trace is non-zero only if you have a periodic orbit. So we have proven this formula. So on the left-hand side, you have this delta function, the spectral points, Kn. And on the right, you have certain geometric topological information. This is the sum over all periodic orbits. And this sum is infinite, because if you go along one periodic orbit once, then you can go also to 2024 times, and so on. So this is the total length of the graph, the sum of the lengths. And this is the Euler characteristic of the graph. Roughly speaking, this is the number of independent cycles of the graph. So this formula was suggested by physicists, but somehow without real proof, and also some terms were missing here. So we proved it with my PhD student Novachuk, and I think that Marko was an opponent in this defense. Okay, so this formula reminds of Guillemin-Melrose trace formula for Riemannian manifolds, but there is a big difference. So in this formula, you have, this corresponds, roughly speaking, to the left, this corresponds to this sum, but then there is a correction term which is an L1 function. And this delta function is somehow embedded into this L1 term. For physicists, delta function is an L1 function. It's very close. But I realized that this formula should also be written, can also be written in a different way. We simply move this term which contains Euler characteristic from the right to the left, and you get this formula. And what you get here? On the left, you have a sum of delta functions with certain coefficients, positive. And on the right, you have constant. Fourier transform of the constant is a delta function. Yes? And then there is a sum over some coefficients, and there are cosine. Cosines are exponentials. Yes? Sum of two exponentials. Fourier transform of exponentials are delta functions. So it means that the right-hand side is again a sum of delta functions. The Fourier transform of the right-hand side is a sum of delta functions, but delta functions have support at the lengths of the periodic orbit on this graph. And this sum is also infinite. So it means that this is a crystalline measure. I felt that there was something interesting with this. So in 2005, we wrote a letter to Kahan and asked him about that observation. And his answer was like playing with Poisson formulas in several dimensions gives a lot of formulas on the line. He pointed to these Millet sets. Yes, he didn't realize that this example was very special, and I didn't thought in this direction for 10 years. But 2018, Yves Millet came to Stockholm, gave a lecture at Mittag-Leffler Institute, and he presented an extremely complicated example of a crystalline measure, following the paper by Guénon. Yes. And I was sitting in the audience, and I had an example of explicit crystalline measure. I went to him after the lecture, and he didn't believe this. He said that probably your example is just finite combination of usual Poisson summation formulas. No, and this guess was completely correct, because in the graph you have finitely many intervals. It's a good guess. But in order to explain why it is not, I need a little bit more. So you see, I told you that these H scattering metrics depends on the lengths of the edges. So in this form, it depends on the exponential. So let us, instead of the exponential e to the power I k ln, put zeta n, a complex parameter. Yes? Then instead of the trigonometric polynomial, you get a usual polynomial in n variables, multivariate polynomial, yes? So, which we call secular polynomial. It's after Barra-Gaspar paper. So this polynomial has the following properties. The first thing, that this is a second order in each variable, because in each variable appears only at two places. Yes. So then it's stable. The definition of the stable is a little bit later, but stable polynomial means that it has no zeros inside the unit disk. So when all zetas have absolute value less than 1, there are no zeros. And then it's also invariant under involution. Involution means that if instead of every zeta I put 1 over zeta, and then multiply by product of zetas, I get the polynomial back. It has such nice properties, yes? So of course, it depends only on the discrete graph, because we eliminated the lengths now. And in order to get the spectrum of the metric graph, you have simply to put into this polynomial these exponentials back. So one can think about getting the spectrum of these graphs in the following way. So, for example, you have a polynomial, a graph with two edges, yes? And this is the zero set of this polynomial, yes? Of this multivariate polynomial. And then you take a curve or a line with the angle L1, L2. So it means that in two variables somehow this angle is equal to the ratio L2 to L1. So, and you see, since I'm using here the real representation of the torus, yeah? So it's just a straight line. When this straight line meets the zero set, you get a eigenvalue. It means the second one, second eigenvalue. But then it continues. And if this angle is irrational, and this is interesting case, when it is irrational, then this line covers the torus, and you get infinitely many points. If the angle is rational, yes, then the picture is periodic. And this formula becomes a trivial sum of Poisson summation formulas. Okay, for example, if you have such a graph with three edges, then you can see that the corresponding polynomial will be like this. If you have a loop, you will get a first order factor, but the rest is irreducible polynomial in the other variables. So here, for example, is the zero set of this guy. So now the picture is more complicated. Yes, so this blue plane, this corresponds to this first factor, zeta 3 minus 1, yes? But the rest is the zero set of this complicated factor, yes? And here you again should draw a line with in a three-dimensional space when it meets this this surface zero set, you get eigenvalues. So more generally, one can prove the following theorem, that if you have a general metric graph, then the corresponding polynomial is a product of first order factors corresponding to loops. How many loops? So many factors times something which is irreducible. This was a hard part. Or if the graph is a watermelon graph, then the corresponding polynomial is a product of first degree polynomials in each variable. Okay. So the first example of crystalline measure. You take the simplest graph, absolutely the simplest graph. This is a lasso graph, or lasso graph. Yes, and then you eliminate the first trivial factor. And this polynomial is stable. Why is stable? Here it's elementary because P of z is equal to 0 is equivalent to this relation. And this is a Möbius transform that maps a unit disk outside the unit disk. Yes, and so it means that if zeta1 is less than 1, then zeta2 must be greater than 1, or absolute value. Then it's also invariant under involution. So everything is, what I said. And this, actually, this picture that I showed you, it was the picture corresponding to this graph, yes? So, and then you get this equation describing the spectrum of this graph, yes? Non-trivial spectrum of the graph. And then you can see that this spectrum is uniformly discrete, because there is always a distance between two subsexual intersections between the line and this zero set. So, meaning this is uniformly discrete and relatively dense. So then there is a summation formula. I just put it here in order to illustrate that how does it look like, that the sum of h at k at the spectrum is equal to the sum of the Fourier transforms at the lengths of periodic orbits, because you see periodic orbits on this graph, how they can be achieved. You go, for example, once along this loop, then you have to go twice along this one. So therefore, in this formula, you have sums of n1 L1 plus 2n2 L2. Yes? And this is a completely explicit formula. So, but how to prove that this is not but how to prove that this Kj don't belong to a finite sum of arithmetic sequences? Yes. So Peter Sarnak, he suggested one proof, but later on I came with a very simple theorem that it says the following thing, that if you have uniformly discrete finite combination of Dirac combs, then it's periodic. Simply somehow, if you have a finite combination of Dirac comps, it cannot be non-periodic. And this equation is non-periodic. Therefore, its zeros are not periodic. This is obvious. So it means that this is really a finite, it's not a finite combination of Dirac comps. So as Peter told that mathematics is simple, one should only understand why. So, and this example now gives you a positive crystalline measure, which is not a generalized Dirac comp. It's a positive Fourier quasicrystal. So it means that not only mu, but also absolute value of mu, absolute value of mu hat are temporal distributions, and also a lot of other questions. So what was the solution by Peter? So I formulated the following question. Consider the trigonometric equation where A is non-rational. Because if A is rational, then the solutions are periodic. Interesting case when A is irrational. And then prove that if you take a linear combination with rational coefficients of Kn and take a dimension with respect to Q, then it's infinite. Then this is not this guarantees that it's not a set of, it's not a sum of Poisson formulas with different, not a finite sum of Poisson formulas. And ask this question to at least 50 mathematicians. Some of them are sitting here. I just saw them walking in, but now I cannot find them. But, and then it was answered by Peter, and actually he realized that there was a connection to so-called Lang's conjecture. But this is a theorem, so it's proven. So suppose that you have an algebraic variety on a torus, yes? And then you have a finitely generated subgroup on the torus of multiplications, yes? And then you consider division group. Division group, these are all elements such that some power of these elements belong to the original group. And then it was proven that intersection between this division group and the variety is along a finitely many tori. So it means that you don't need to consider the whole variety. You need only to consider certain tori. Yes, and the number of toris can be estimated explicitly. It's a long formula, but it's not. Yeah. So how this can be applied to this question that I ask? Simply, if you suppose that this dimension is finite, so it means that there is a certain n0 such that all kn's are rational combinations of the first n0 case. Yes. So if you write it in the multiplicative way, you get it like this. So which means that all these exponentials, they belong to the division group for the multiplicative group generated by the first n0 numbers. Yes? And it feels like this Lang's conjecture was proven especially to serve our purposes. Actually, I don't know where it was applied in a different way. So, but all hypertori for our graphs are all hypertori. They are described by such equations. And in our case, they are only of this form, corresponding to these loops, zeta n minus 1. There are no other hypertori, because one can have lower hypertori, but if you assume that the lengths are rationally independent, then the line can intersect a lower dimensional hypertori only once. So there are some exceptions, but this is not important. So it means that this Lang's conjecture helps us to prove that this dimension is infinite. So, but moreover, that the spectrum doesn't, if there are no loops, doesn't contain infinite arithmetic progressions. All infinite arithmetic progressions comes from the loop factors. Yes? In non-loop factors, there could be finite arithmetic progressions, but the number of elements in a finite arithmetic progression could be also bounded by some number, by this constant C that exists in this Lang's conjecture. So it means that this is a complete description of the arithmetic structure of the spectrum. So we also got it. And then when we try to generalize this, because somehow, you see, before it was just these graphs, but how can you generalize it in a more, how can you do it better, yes? Then, so we realize the following thing, that one should start simply directly from a multivariate polynomial, and you require that it is stable. Stable means no zeros in the unit disk, and then it's invariant under involution. Yes? Then we also assume some normalization condition, which is not so important. Such polynomials are called Lie-Yang polynomials. And then if for these Lie-Yang polynomials you introduce a Dirichlet series by this formula. So it's the same as in these metric graphs. The only thing that now there are b's to the power s, so there is no i's there. So therefore this f now has zeros not on the real axis but on the imaginary axis. And then you repeat the same proof as was done for metric graphs, the same proof of the trace formula. And you get summation formula for these stable polynomials. So after this has been done, so there was some activity in this area. For example, Meyer, he published something like 5 papers where he put this example into different constructions that he tried to make. Because trying to solve the problem, he of course developed several techniques, and now he put it in. So, for example, he introduced curved model states instead of, I don't know, the old ones model sets, which were, yeah. So then Olevsky, Ulanovsky, they decided to go a slightly different way. So they realized that, you see, we had metric graphs, then there were trigonometric polynomials, no, then there were multivariate polynomials, which are stable, Lie-Yang, and then we came to trigonometric polynomials with real coefficients, with real zeros. Then they decided to start just from the trigonometric polynomials with real zeros. Then they proved the theorem that all Fourier quasicrystals in one dimension with integer mass, positive integer masses can be given by exponential polynomials with only real zeros. But these 3 guys, Alon, Cohen, and Vincent, they proved that all trigonometric polynomials with real zeros come from our construction with Sarnak, which means that the construction is general enough to describe all such crystalline measures. Okay, so now what about several dimensions? You see, here there were 2 possible generalizations of this. One was to start generalizing our construction, or to look directly at systems of trigonometric equations in several variables that have only real solutions. This was tried by Meyer. We are doing this with the Kursi Island in Stockholm, and then there is a recent preprint by Lauten and Zich. But today I will try to explain what we did with these young guys. Let us go back. This is discharged. It is?
the handheld one. Sorry about that.
So you see, it puts extra emphasis on this last part. No. I don't know. No. Okay. So, sorry for this. So let us go back to this one-dimensional case. Yes. So there was a Lie-Yang stable polynomial. Yes, and it was stable and also invariant under involution. It means that it didn't have zeros inside the unit disk, and it didn't have zeros outside the unit torus. Yes? So consider the logarithm of absolute value function defined like this. You take a logarithm of each variable. Then the zero set of this polynomial avoids r minus to the power n and r plus to the power n, because this the unit disk by this function is mapped to r minus to the power n, and this star is mapped to r plus to the power n. Yeah, so it means that if you look at what happens after this logarithm, that the zero set avoids two quadrants. Yes, and then you obtain Fourier quasicrystal by plugging in these exponentials. For some reasons, 2 pi appeared here, but it's not so important. Mm-hmm. Okay, so how to do it in several dimensions? So first of all, we introduce so-called Lie-Yang variety. Lie-Yang variety of dimension C, yes, is a variety which is invariant under involution, yes, and for every zeta we have either that zeta belongs to the torus, yes, or the variation of logarithm of zeta is greater than d. Variation is how many times these numbers change the sign. If you have a sequence of real numbers, some of them are positive, some of them are negative, then they change sign. So this number of changes should be at least d. And then there is a technical condition that the intersection with the torus is contained in the smooth part of X. So what we take as an analog of the vector L? L was a vector of the lengths, yes? Now we take a matrix, n times d matrix, all whose minors are positive. Yes? And then this set lambda in CD, this is the set everywhere there. If you apply LZ and then exponential, then it belongs to X. So this is the same as in one dimension. And then the theorem is the following: that first of all, this intersection is real. So it is in RD, not CD. Then it's a Delaunay set, and it's a Fourier quasicrystal. So this is for any dimension d or greater than 1. And it's more general than Meyer's or Lawton-Zich constructions, because they considered only Fourier quasicrystals which are defined by in dimension, for example, 2, they're defined by 2 trigonometric polynomials. But now we can have more general situation. So now I think I skip these things. I will show you examples. So, and the example is the following. So we take a variety described by these 2 polynomials. Yes? And then you take a linear map L given by this matrix. So let us calculate the 2 by 2 determinants here. This is 1. If we take this, and this is square root of 3. If we take this, the determinant will be square root of 2 again. So they are positive. So here it's important to understand that this definition of Lie-Yang variety depends on the order of the coordinates. But also positivity of these determinants also depends on the order. So they compensate each other. So, and here there is an example. So the blue curve, this is the variety, yes, and then it intersects the orange plane, which is the range of this matrix L. And when they intersect, we get a point. So, or you can have a look at this picture. So I think I prepared better picture. So these are two trigonometric polynomials, and common zeros of these polynomials, they give Fourier quasicrystal. And you can see that there is no periodicity, clear periodicity, and they are uniformly discrete. But if you look at the Fourier side, then this is a support of mu hat, yes, and then it has such a form. So it's also no periodic structure and so on. But then this is not uniformly discrete, because this theorem by Lev Olevsky tells that if both are uniformly discrete, then these are finite combinations of Poisson summation formulas. And then also I decided I will make some kind of contribution to the modern art. So this is another example that exists in our paper. So here the crystalline measure of Fourier quasicrystal is given by the points where all three. So these curves are zeros of three trigonometric polynomials, yes? And only when all three are zero, this gives us points supporting this Fourier quasicrystal. I don't know, we are looking where to send this picture. And then somehow, thank you for your attention, but I wanted to make some kind of advertisement of my book. So the major part of the first part of the talk is contained there. Therefore, I had to rewrite it for the third time. Okay, thank you for your attention.
Okay, thank you very much, Pavel. Are there any questions?
Yes?
Can you hear me?
Yes?
So there are other famous trace formations, silver trace formation. Can you say is there any relationship to the trace formation?
No, it's different.
But maybe its graphs can be rather dense and
No, but they're different. But I could not find a way from Selberg trace formula to this one.
Okay, any other questions? Yeah, there's one there. John.
You described quantum graphs with standard vertex conditions. Do the vertex conditions make any difference for that?
So you see that if the vertex conditions are so-called scaling invariant, so which means that the vertex scattering matrices don't depend on the energy, then I can do the same. Yes, there is no difference. But when they start depending on the energy, there will be some differences. But
okay, so let's thank Pavel for the talk again.